Hello and welcome to Space Historians. I'm glad you've joined me, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Each episode here isn't just about stars, it's about the stories they hold, the mysteries whispered by ancient astronomers, and the quiet mysteries still waiting. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. Imagine holding a teaspoon. In your hand, it weighs almost nothing. A few grams perhaps, light enough to lift without thought, to carry without effort. Now, imagine filling that teaspoon with matter from a neutron star. Suddenly, impossibly, it weighs as much as a mountain. Not a hill, not a boulder, but an entire mountain. All the mass of Everest, compressed into a volume you could hold in your both palm. If you tried to set it down, it would tear through the floor, through the foundation, through bedrock. It would sink toward the center of Earth, unstoppable. The planet itself could not support its weight. This is not science fiction. This is the reality of neutron stars, the densest objects in the universe that aren't black holes. To understand how such a thing is possible, you must first abandon everything you think you know about matter. On Earth, matter feels solid because of the space between atoms. When you touch a table, you are feeling electromagnetic forces pushing back against your hand. But most of the table is empty space. The nucleus of an atom is tiny compared to the cloud of electrons surrounding it. If you could remove that empty space, compress the atoms until their nuclei touched, the table would shrink to the size of a grain of sand, and it would weigh exactly the same. A neutron star takes this compression to an extreme that defies comprehension. It is what remains after a massive star dies, after it exhausts its nuclear fuel and collapses under its own gravity. The outer layers explode outward in a supernova. The core implodes inward, crushed by forces so overwhelming that atoms themselves are destroyed. Protons and electrons are squeezed together, forming neutrons. The result is a sphere roughly 20 kilometers across, no larger than a city, yet containing more mass than the Sun. That is the impossible beginning. Not impossible in the sense of fantasy, but impossible in the sense that it stretches human imagination to the breaking point. Numbers cannot capture it. Analogies fail. A teaspoon of neutron star matter weighs 1 billion tons. A sugar cube weighs as much as humanity. The surface gravity is 200 billion times stronger than Earth's. Drop something, and it would strike the surface in less than a microsecond, releasing energy equivalent to a nuclear explosion. And yet, neutron stars exist. Millions of them, scattered throughout the galaxy. Most are invisible, dark and silent, drifting through space like cosmic ghosts. But some reveal themselves. They spin, sometimes hundreds of times per second, sweeping beams of radiation across the void. They are lighthouses in the darkness, pulsars, announcing their presence with rhythmic precision. Others erupt in violent flares, magnetic fields so strong they distort the very fabric of space. These are magnetars, the most extreme neutron stars, capable of releasing more energy in a fraction of a second than the Sun emits in 100,000 years. To stand on the surface of a neutron star would be to experience gravity so intense that your body would be stretched and torn apart before you could take a breath. The difference in gravitational pull between your head and your feet would be so great that you would be ripped into atoms. This is called spaghettification, a term that sounds almost whimsical until you understand what it describes. It is death by tidal forces, by the uneven grip of gravity, pulling harder on one part of you than another. But you cannot stand on a neutron star. You cannot even approach one. The radiation alone would kill you from thousands of kilometers away. X-rays, gamma rays, particles accelerated to near light speed, all streaming outward from the surface. The magnetic field, in the case of a magnetar, would be strong enough to disrupt the atoms in your body, to alter the shape of electron orbits, to make chemistry itself behave differently. You would not survive long enough to feel the gravity. And yet, from a safe distance, neutron stars are not hostile. They are simply extreme. They are nature's way of showing what happens when matter is pushed to its absolute limit, when gravity becomes so strong that nothing can resist it except the fundamental laws of quantum mechanics. Neutrons, packed shoulder to shoulder, push back against further compression. This resistance, called degeneracy pressure, is what prevents the neutron star from collapsing into a black hole. It is the last stand of matter before it disappears behind an event horizon. The impossible beginning is also a story of transformation. A massive star, glowing brightly for millions of years, ends its life in a catastrophic explosion. What remains is not darkness, but something new. A neutron star is a phoenix born from fire, a remnant that refuses to vanish entirely. It is smaller than the star it came from, denser, stranger, but still present, still exerting gravity, still spinning, still radiating, still shaping the space around it. This transformation is not gentle. It is violent, sudden, complete. In the span of a few seconds, a star's core collapses from the size of Earth to the size of a city. The implosion releases more energy than the star emitted during its entire lifetime. The outer layers are blown away at tens of thousands of kilometers per second, and in the center, crushed beyond recognition, is the neutron star. Silent, dark, waiting. The impossible beginning is also a reminder of scale. We live in a universe where a teaspoon of matter can weigh 1 billion tons, where gravity can bend space and time, where stars can collapse into objects so dense that their surface is stronger than steel, harder than diamond, more rigid than anything we can imagine. And yet these objects are not rare, they are common. They are the natural endpoint for stars massive enough to collapse but not massive enough to become black holes. To think about neutron stars is to confront the limits of human experience. We cannot hold them, touch them, visit them. We can only observe them from afar, measure their signals, infer their properties. And in doing so, we learn that the universe is far stranger than it appears. That matter can be compressed into forms we cannot create on Earth. That density has no upper limit short of a black hole. That even in death, stars can be extraordinary. This is the impossible, beginning. A teaspoon that weighs a mountain. A city that weighs more than the sun. A star that died and became something else. Something denser, something deadlier, something utterly unlike anything in our everyday world. And it is real. Proven by observation, confirmed by theory, woven into the fabric of the cosmos. 1934. The world was still recovering from the Great Depression. Radio was the cutting edge of communication. The structure of the atom was barely understood. And in that year, 2 astronomers proposed something that seemed impossible. They suggested that when massive stars collapse, they might not disappear into black holes or fade into obscurity. Instead, they might become something new, something so dense that atoms themselves would be crushed into pure neutrons. The idea came from Walter Beatty and Fritz Zwicky, working at the California Institute of Technology. They were studying supernovae, the brilliant explosions of dying stars. Supernovae were mysterious events, rare and poorly understood. Beatty and Zwicky wanted to know what caused them. What could make a star suddenly brighten to rival an entire galaxy, then fade back into darkness? Their answer was radical. They proposed that supernovae were not just explosions, but collapses, that the core of a massive star, having exhausted its nuclear fuel, would implode under its own gravity. The implosion would be so violent that it would trigger an explosion in the outer layers, blasting them into space. And what remained at the center, they suggested, would be a neutron star. The name itself was new. Neutrons had only been discovered 2 years earlier, in 1932, by James Chadwick. They were particles with no electric charge, roughly the same mass as protons, found in the nuclei of atoms. Bardet and Zwicky proposed that under extreme pressure, all the protons and electrons in a star's core could be squeezed together to form neutrons. A star made entirely of neutrons, packed so tightly that a cubic centimetre would weigh millions of tons. It sounded like science fiction, and to most astronomers, it was. The idea was too extreme, too far removed from anything observed. Stars were made of hydrogen and helium, glowing hot and bright. The notion that one could collapse into a ball of neutrons seemed absurd. Without evidence, the proposal was filed away. Interesting in theory, but impossible to test. For decades, neutron stars remained a footnote in astrophysics. They were mentioned in textbooks as a theoretical possibility, but no one expected to find them. The technology did not exist to detect them. Telescopes could see bright stars, galaxies, nebulae, but a neutron star, only 20 kilometers across and emitting little visible light, would be invisible. It would be a needle in a cosmic haystack, too small and too faint to notice. Yet the theory persisted. In the 1930s, 40s, and 50s, physicists continued to explore the idea. They calculated what would happen to matter under extreme pressure. They modelled the collapse of stellar cores. They refined the equations governing density, gravity, and nuclear forces. Slowly, a picture emerged. If a star's core was massive enough, it would collapse past the point where electrons could support it. But if it was not too massive, it might stabilize as a neutron star, held up by the pressure of neutrons resisting further compression. This was not idle speculation. It was grounded in physics, in the same principles that explained atomic nuclei and the behavior of matter under pressure. But it was still theoretical. No one had seen a neutron star. No one knew if they truly existed outside of calculations. The setting of this story is important. The 1930s were a time of rapid discovery in physics. Quantum mechanics was revolutionizing the understanding of atoms. Relativity was reshaping the understanding of space and time. Nuclear physics was revealing the forces that held matter together. In this environment, the idea of a neutron star fit naturally. It was an extension of known principles into extreme conditions. But it was also a time of caution. Science had been wrong before. Ideas that seemed logical in theory sometimes failed when tested by observation. Without evidence, neutron stars were just an idea, a curiosity, a prediction waiting to be confirmed or dismissed. The human element here is crucial. Bardet and Zwicky were not just proposing an abstract concept. They were trying to explain real phenomena. Supernovae had been observed for centuries, sudden new stars appearing in the sky, blazing brightly, then fading. What caused them? Where did the energy come from? The collapse of a stellar core into a neutron star, Bardet and Zwicky argued, could release enough energy to power a supernova. The implosion would be so violent that the rebound would blow the outer layers into space at thousands of kilometers per second. It was a bold claim, and it was largely ignored. Zwicky, in particular, was known for being difficult, combative, convinced of his own brilliance. His ideas were often dismissed, not because they were wrong, but because he was hard to work with. Bardet was more diplomatic, but even he could not overcome the skepticism. Without evidence, their proposal remained speculative. And so the years passed. The 1940s brought World War II, shifting scientific focus toward radar, nuclear weapons, and rocketry. The 1950s saw the dawn of radio astronomy, with large antennas listening to the sky for signals beyond visible light. But still, no neutron stars were found. The theory remained in the background, mentioned occasionally, but not pursued with urgency. It is worth pausing to consider how fragile knowledge can be. Bardet and Zwicky were right. Their idea, proposed in 1934, would eventually be confirmed, but it took more than 30 years for the evidence to arrive. In the meantime, their proposal could have been forgotten entirely. Science does not always reward the first person to think of something. It rewards the person who proves it. The setting also shapes the story. In the 1930s, astronomy was limited by technology. Telescopes were improving, but they could only see visible light. The universe beyond that spectrum, the radio waves, X-rays, gamma rays, was invisible. Neutron stars, as it turned out, shine brightly in these invisible wavelengths. But without the tools to detect them, they remained hidden. This is where it all began. Not with a discovery, but with an idea. Not with evidence, but with theory. Two astronomers, working at the edge of knowledge, proposed that stars could collapse into objects so dense that atoms would be destroyed. They had no proof. They had only equations, logic, and the courage to propose something that sounded impossible. And for 30 years, the universe kept its secret. Neutron stars, if they existed, remained invisible. The idea lingered in the background of astrophysics, waiting for the moment when technology would catch up with theory, waiting for someone to find the signal that would prove Bardet and Zwicky right. This is the origin story. Not of neutron stars themselves, which had existed for billions of years, but of humanity's awareness of them. It began in 1934, with a proposal so bold it seemed absurd, and it would not be confirmed until 1967, when a graduate student listening to the radio sky heard something no one expected. A pulse. Regular, precise, impossible to ignore. 1967. Cambridge, England. A graduate student named Jocelyn was monitoring data from a new radio telescope. The instrument was crude by modern standards, an array of wooden poles and copper wire spread across several acres. It had been built to study quasars, distant galaxies emitting powerful radio waves. But on a quiet afternoon in November, Bell noticed something unusual in the data. A signal, regular, repeating, arriving with astonishing precision. At first, she thought it was interference. Radio telescopes are sensitive instruments, easily disrupted by human activity. Car ignitions, electrical equipment, even the spark from a faulty wire can create false signals. Bell checked the equipment, traced the cables, looked for sources of contamination, but the signal persisted. It arrived every 1.337 seconds, like clockwork, never varying, never fading. She brought it to the attention of her supervisor, Anthony Hewish. Together, they ruled out terrestrial sources. The signal did not come from Earth. It came from a fixed point in the sky, rising and setting with the stars. This meant it was astronomical in origin, something out there in space, sending pulses toward Earth with mechanical regularity. The precision was what puzzled them most. Natural phenomena are rarely so regular. Stars flicker, galaxies vary. Even the rotation of planets has minor wobbles. But this signal was steady, predictable, repeating with an accuracy that rivaled atomic clocks. It seemed almost artificial, as if someone or something was transmitting a signal deliberately. The team began to wonder, could it be extraterrestrial intelligence? The idea seemed far-fetched, but the evidence was hard to dismiss. A signal arriving from deep space, pulsing with perfect rhythm, unlike anything seen before. They jokingly labelled it LGM-1, short for Little Green Men. The name was tongue-in-cheek, But the question was serious. If this was not natural, what was it? Bell continued to monitor the signal. She searched the data for other examples, scanning through miles of paper charts covered with ink traces. And she found them. More signals from different parts of the sky, each pulsing at its own unique rate. One every half second, another every few seconds. Some fast, some slow, but all regular, all precise, all inexplicable. This was the spark of mystery. Not one anomaly, but many. Not a fluke, but a pattern. Something in the universe was producing these signals, and it was not unique to one location. It was widespread, scattered across the sky, waiting to be discovered. The discovery changed everything. If these signals were natural, they represented a new class of astronomical object. Something never predicted, never imagined. If they were artificial, they were evidence of intelligence beyond Earth, perhaps civilizations far more advanced than ours. Either way, the implications were staggering. Hewish and Bell published their findings in February 1968. The paper was cautious, describing the signals without speculating too much about their origin. They called them pulsating radio sources, shortened to pulsars. The name stuck. Within months, other astronomers confirmed the discovery, finding more pulsars with their own radio telescopes. The mystery deepened. What could produce such signals? The regularity suggested rotation. Something spinning, sweeping a beam of radiation across space like a lighthouse. But what? A planet could not spin fast enough. A normal star would fly apart if it tried. Only something incredibly dense, incredibly compact, could rotate hundreds of times per second without breaking apart. The answer came quickly. Within a year, theorists proposed that pulsars were neutron stars, the collapsed cores of massive stars spinning rapidly, emitting beams of radiation from their magnetic poles. As the star rotated, the beams swept across Earth, producing the pulses. It was elegant, simple, and it explained everything. The regularity, the speed, the radio emissions, all fit with the properties of neutron stars predicted decades earlier by Bade and Zwicky. The spark of mystery had ignited a revolution. Neutron stars, once theoretical curiosities, were now observational facts. They existed, they were real, and they were nothing like anyone had imagined. Not silent, dark remnants drifting invisibly through space, but active, pulsing, radiating, announcing their presence across light years. Bell's discovery was accidental in one sense. She had not been looking for neutron stars. She had been studying quasars. But science often works this way. You build an instrument to answer one question, and you stumble upon something else entirely. The universe does not reveal its secrets on demand. It reveals them when we are paying attention. The spark of mystery also revealed something about human curiosity. When faced with the unknown, we do not turn away, we investigate, we question, we search for answers. Bell could have dismissed the signal as noise, as interference, as a glitch in the equipment, but she did not. She followed the evidence, even when it led somewhere unexpected. The discovery also highlighted the importance of tools. Without the radio telescope, the pulsars would have remained invisible. Visible light telescopes cannot detect them. They do not shine brightly in optical wavelengths. But in radio waves, they are beacons, unmistakable, impossible to ignore. This is why astronomy has expanded beyond visible light. The universe speaks in many languages, and we must listen in all of them. The spark of mystery was not just about neutron stars. It was about the process of discovery itself, about noticing patterns, asking questions, following evidence, about the moment when something unknown becomes known, when theory becomes observation, when speculation becomes fact. Jocelyn Bell did not receive the Nobel Prize for her discovery. That honour went to Hewish, her supervisor. The omission has been debated ever since, a reminder that science is not always fair, that credit does not always go to those who deserve it. But Bell's role in the discovery is undeniable. She noticed the signal. She pursued it. She found others. Without her, the story might have unfolded differently. The spark of mystery also changed how we think about the universe. Before pulsars, neutron stars were theoretical. After pulsars, they were mapped, catalogued, studied in detail. Each one became a laboratory for extreme physics, a place where matter behaved in ways impossible to replicate on Earth. The discovery opened doors that had been closed for decades, and it raised new questions. If neutron stars could spin hundreds of times per second, what powered them? How did their magnetic fields generate radiation? How did they form? How many existed in the galaxy? Each answer led to more questions. Each discovery to more mysteries. This is the spark. The moment when the unknown becomes visible. When a signal arrives, regular and precise, and the world changes. When theory meets observation, and both are transformed. When a graduate student, listening carefully to the radio sky, hears something that should not be there. And when that something turns out to be one of the most extraordinary objects in the universe. The discovery of pulsars sent shockwaves through the scientific community. When Hewish and Bell announced their findings in early 1968, the response was immediate and divided. Some astronomers were awed, recognizing instantly that this was a major breakthrough. Others were skeptical, questioning whether the signals were truly astronomical or simply some form of sophisticated interference. The regularity of the pulses was the source of both wonder and doubt. Nothing in nature, as far as anyone knew, could produce such precise timing. Stars flickered, galaxies varied, even the most stable processes showed some irregularity. But the pulsars did not. They pulsed with a consistency that rivaled, and in some cases exceeded, the best atomic clocks. For some, this was evidence of something extraordinary. For others, it was evidence that the signals must be artificial. The little green men hypothesis, though half joking, was taken seriously enough to warrant investigation. If these were signals from extraterrestrial civilizations, what did that mean? The implications were staggering. Contact with alien intelligence would be the most profound discovery in human history, reshaping philosophy, religion, science, and culture. The possibility could not be dismissed lightly, but the evidence against the hypothesis mounted quickly. First, there was not one signal, but many. Jocelyn Bell had found 4 within weeks, each from a different part of the sky, each pulsing at a different rate. If these were alien transmissions, it implied multiple civilizations, all broadcasting at the same time, all using similar technology. Possible, but unlikely. Second, the signals were simple, just pulses. No modulation, no encoded information, no variation in pattern. If an advanced civilization wanted to signal its presence, surely it would send something more complex than a repetitive beep. The simplicity suggested a natural phenomenon, something governed by physics rather than intent. Third, the locations were random. The pulsars were scattered across the sky with no apparent pattern. If they were beacons meant to attract attention, one might expect them to cluster near bright stars or other obvious landmarks. But they did not. They appeared wherever massive stars had died, which was everywhere. As the evidence accumulated, the extraterrestrial hypothesis faded. What remained was awe at the natural explanation. If these were neutron stars, then the universe was even stranger than anyone had imagined. Stars could collapse into objects so dense that a teaspoon of their matter would weigh 1 billion tons. And those objects could spin hundreds of times per second, fast enough to complete a rotation in the blink of an eye, without flying apart. It was almost as hard to believe as aliens. The disbelief came from physicists who struggled to accept the extreme conditions implied by neutron stars. How could matter be compressed to such densities? What held it together? The equations suggested it was possible, but equations were abstractions. The real universe, messy and complicated, did not always follow theoretical predictions. Some argued that the pulsars must be something else, some other kind of object not yet understood. Others pointed out that neutron stars had been predicted decades earlier. Bardet and Zwicky had proposed them in 1934. The theory existed. The physics was sound. The discovery of pulsars simply confirmed what had been suspected all along. To these astronomers, the surprise was not that neutron stars existed, but that they had remained hidden for so long. The awe came from recognizing the power of observation. For 30 years, neutron stars had been invisible. Then, with a new instrument, listening in a new wavelength, they suddenly appeared. Dozens of them, then hundreds, scattered across the galaxy. It was a reminder that the universe is always larger, always stranger than our current instruments can reveal. The discovery also inspired a sense of wonder at the scale of cosmic violence. Neutron stars were born in supernovae, explosions so powerful they could outshine entire galaxies. The fact that anything survived such an event, let alone something as structured and stable as a neutron star, was astonishing. These objects were not just remnants, they were monuments to the death of stars, testaments to the resilience of matter under extreme conditions. Public reaction was mixed. Newspapers reported the discovery, often sensationalizing it. Headlines spoke of mysterious signals from space, of possible alien contact, of cosmic lighthouses. The truth was less dramatic, but no less fascinating. Pulsars were natural, but they were also extraordinary. They pushed the boundaries of what seemed possible. Among scientists, the discovery sparked a rush of activity. Radio telescopes around the world began searching for more pulsars. Each new discovery added to the broad catalogue, revealing patterns and variations. Some pulsars were fast, spinning hundreds of times per second. Others were slow, pulsing only once every few seconds. Some were bright, easily detected. Others were faint, barely visible above the noise. The awe also came from the precision of the measurements. Astronomers could time the pulses to within microseconds, tracking changes over months and years. This precision allowed them to study the pulsars in extraordinary detail. They could measure how fast the stars were spinning, how quickly they were slowing down, how their magnetic fields were aligned. Each measurement revealed something new about the physics of extreme density. Disbelief lingered in some quarters. A few astronomers continued to search for alternative explanations, unwilling to accept that neutron stars could behave as the observations suggested. But the evidence was overwhelming. The pulses matched the predictions of rotating neutron stars too closely to be coincidence. The models worked. The theory fit the data. Slowly, the skeptics were convinced. The discovery also had a human dimension. Jocelyn Bell, the graduate student who first noticed the signal, became a figure of both admiration and controversy. Her role in the discovery was undeniable, yet she was not included in the Nobel Prize awarded to Hewish. The omission sparked debate about recognition, credit, and the role of graduate students in scientific discovery. Bell herself handled the situation with grace, continuing her career in astronomy and later speaking about the importance of encouraging young scientists. The awe and disbelief were not opposites. They coexisted. Scientists could be skeptical of extraordinary claims while also marveling at the implications if those claims were true. The discovery of pulsars embodied this tension. It was too strange to accept easily, yet too well supported to dismiss. And in the end, the awe won. The universe had revealed something new, something unexpected, something that expanded the boundaries of knowledge. The discovery of pulsars answered one question but raised many others. If these were neutron stars, how exactly did they produce such regular pulses? And more fundamentally, how could a neutron star exist at all? The contradiction at the heart of the mystery was profound. Stars collapse under gravity. But gravity, if unchecked, should crush matter into a black hole. How could a neutron star stop halfway, stabilizing at a density just short of infinite? The answer lay in quantum mechanics, the physics of the very small. At ordinary densities, atoms are held apart by electromagnetic forces. Electrons orbit nuclei, and when atoms are pressed together, their electron clouds repel each other. This is why solid matter resists compression. But under extreme pressure, this resistance breaks down. Electrons are forced into the nuclei, combining with protons to form neutrons. The result is a sea of neutrons, packed tightly, together. Neutrons, like all particles, obey the Pauli exclusion principle. This principle states that no two neutrons can occupy the same quantum state. As neutrons are compressed, they fill up the available states, and further compression requires forcing them into higher energy states. This creates a pressure, called degeneracy pressure, that resists further collapse. It is not a force in the ordinary sense, but a consequence of quantum rules, and it is strong enough in the right mass range to hold up a neutron star. This was the science. The equations worked. The physics was sound, but it stretched intuition to the breaking point. How could something with no force, just a statistical rule about particles, hold up the weight of a star? It seemed too abstract, too removed from everyday experience. And yet, the observations confirmed it. Neutron stars existed. They were stable. They did not collapse into black holes. The mystery lay in the details. What exactly happened inside a neutron star? The outer crust, perhaps a kilometer thick, was thought to be a solid lattice of atomic nuclei, similar to ordinary matter but far denser. Below that, neutrons began to drip free, forming a superfluid, a state of matter with zero viscosity, flowing without friction. Deeper still, the density increased beyond anything that could be tested in a laboratory. Some models suggested that neutrons might break down into their constituent quarks, forming quark matter. Others proposed exotic particles, hyperons or strange matter, governed by forces barely understood. The paradox was that no one could be certain. Neutron stars existed, but their interiors remained hidden. No experiment on Earth could recreate the conditions inside them. The densities were too high, the pressures too extreme. The only laboratory was the neutron star itself, and we could not open it to look inside. All we could do was observe from afar, measuring spins, magnetic fields, temperatures, and inferring the internal structure from those external clues. This tension between science and mystery defined the study of neutron stars. On one hand, they were governed by known laws of physics. Gravity, quantum mechanics, nuclear forces, all applied. On the other hand, they pushed those laws into regimes where predictions became uncertain. The equations allowed for multiple possibilities, and observations alone could not always distinguish between them. The mystery also extended to how neutron stars formed. The theory was clear. A massive star runs out of fuel. Its core collapses. If the mass is in the right range, the collapse halts, and a neutron star is born. But the details were murky. How did the collapse happen so quickly? What triggered the supernova explosion? How did the neutron star end up spinning so fast? These questions required complex simulations, models that pushed supercomputers to their limits. And even then, the answers were approximations, educated guesses. Science and mystery also collided in the behavior of pulsars. The pulses themselves were well explained. A neutron star spins, and if its magnetic poles are not aligned with its rotation axis, it sweeps beams of radiation across space. When those beams point toward Earth, we see a pulse. Simple, elegant, but the details were less clear. How were the beams generated? What accelerated the particles that produced the radiation? Why did some pulsars pulse in radio waves, others in X-rays, and still others in gamma rays? The magnetic fields added another layer of mystery. Neutron stars could have magnetic fields 1 trillion times stronger than Earth's. In the case of magnetars, the fields were even more extreme. How did such fields form? How were they sustained? And what happened when they twisted and snapped, releasing bursts of energy visible across the galaxy? The paradox was that neutron stars were both well understood and deeply mysterious. The broad outlines were clear, the details were not. This is often the case in science. Understanding is not binary. It exists on a spectrum, from complete ignorance to perfect knowledge. Neutron stars occupied the middle ground, known enough to study, mysterious enough to fascinate. The tension also played out in predictions. Some theorists proposed that neutron stars could not exist above a certain mass. Beyond that limit, degeneracy pressure would fail, and the star would collapse into a black hole. But what was that limit? Different models gave different answers. Observations helped narrow the range, but uncertainty remained. Each new discovery, each precise measurement, refined the picture without fully resolving it. Science and mystery are not opposites. They are partners. Mystery drives science. Questions lead to experiments. Experiments lead to answers. Answers lead to new questions. The discovery of pulsars solved the mystery of whether neutron stars existed, but it opened a dozen new mysteries about how they worked, what they were made of, and what they could teach us about the universe. This interplay is what makes neutron stars so compelling. They are not just objects to catalogue and measure. They are puzzles to solve, laboratories to explore, frontiers to push. Every observation adds a piece to the picture. Every theory refines the understanding, but the picture is never complete. The mystery never fully disappears. It simply shifts, deepens, becomes more nuanced. And in that ongoing dance between science and mystery, we find the essence of discovery. Not certainty, but progress. Not final answers, but better questions. Neutron stars embody this process. They are known and unknown, understood and enigmatic, mapped and uncharted. They are the edge of knowledge, the place where science meets the limits of what we can measure and explain. And they remind us that the universe will always hold more than we can grasp. The discovery of pulsars did not immediately unite the scientific community. Instead, it divided them. Astronomers split into camps, each with its own interpretation of the evidence, each defending its position with data, logic, and sometimes stubborn conviction. The question was not whether pulsars existed. The observations were undeniable, but what they were and how they worked. One group argued that pulsars were rotating neutron stars. The theory fit perfectly. A dense, compact object spinning rapidly, sweeping beams of radiation across space like a cosmic lighthouse. The timing of the pulses matched the expected rotation rates. The stability matched the predicted rigidity of neutron star crusts. The magnetic fields matched the theoretical limits. Everything aligned. To these astronomers, the case was closed. Pulsars were neutron stars. The evidence was overwhelming. Another group was skeptical. They questioned whether neutron stars could really spin so fast without flying apart. They doubted whether magnetic fields could be strong enough to produce the observed radiation. They pointed to gaps in the theory, to uncertainties in the models, to alternative explanations that had not been fully explored. Perhaps pulsars were oscillating white dwarfs, vibrating at specific frequencies. Perhaps they were binary systems, two stars orbiting each other and periodically eclipsing. Perhaps they were something entirely new, not yet imagined. The divide was not just about data, it was about philosophy. Some scientists preferred established theories, explanations built on known physics. Others preferred to question everything, to consider exotic possibilities, to avoid premature conclusions. Both approaches had merit. Both had contributed to science in the past. And both clashed when faced with the mystery of pulsars. Thomas Gold, a physicist at Cornell, became one of the strongest advocates for the neutron star interpretation. He published a paper in 1968 arguing that pulsars must be rotating neutron stars. His reasoning was simple and compelling. The pulses were too fast to be orbital. No two stars could circle each other hundreds of times per second without merging. The pulses were too stable to be oscillations. No vibrating object could maintain such precision over months and years. The only explanation that fit all the observations was rotation, and the only object that could rotate so fast without breaking apart was a neutron star. Gold also predicted something remarkable. He argued that pulsars should be slowing down. As they emitted radiation, they would lose energy, and since the energy came from rotation, the spin should gradually decrease. This was testable. If pulsars were neutron stars, their periods should lengthen over time. If they were something else, the periods might remain constant. Within months, observations confirmed Gold's prediction. The Crab pulsar, one of the brightest and fastest known, was slowing down. The change was tiny, only a few microseconds per year, but it was measurable. The spin was decreasing, exactly as the neutron star model predicted. For many, this settled the debate. Pulsars were neutron stars. The evidence was no longer circumstantial, it was direct. But not everyone was convinced. Some argued that other models could also explain the slowdown. Perhaps the radiation was draining energy from oscillations rather than rotation. Perhaps binary interactions were at play. The skeptics did not give up easily. They demanded more data, more tests, more proof. The divide also played out along generational lines. Younger astronomers, trained in the new physics of neutron stars and relativity, embraced the neutron star interpretation quickly. Older astronomers, accustomed to thinking of stars in more familiar terms, were slower to accept. This is a common pattern in science. New ideas often gain traction not because they convince everyone, but because a new generation adopts them while the old generation retires. The disagreements were not always polite. Conferences became battlegrounds, with astronomers presenting competing models and challenging each other's assumptions. Papers were published rebutting earlier papers. Data was reanalyzed, reinterpreted, debated. The process was messy, contentious, sometimes personal, but it was also productive. Each challenge forced proponents to sharpen their arguments, to find better evidence, to refine their theories. One of the key dividing lines was the Crab pulsar itself. Discovered in the Crab Nebula, the remnant of a supernova observed in 1054, this pulsar spun 30 times per second. Its connection to a known supernova provided strong circumstantial evidence that it was indeed the collapsed core of a massive star. But even this was debated. Some argued that the pulsar might be unrelated to the supernova, a chance alignment of unrelated objects. Others questioned whether a neutron star could really form in a supernova, or whether something else was happening. The divide also extended to the mechanism of radiation. How did pulsars produce their beams? The leading model involved magnetic fields channeling particles along field lines, accelerating them to near light speed, and producing radiation through a process called synchrotron emission. But the details were unclear. Where exactly did the emission occur? At the magnetic poles? In the magnetosphere? Along open field lines? Different models gave different answers, and observations could not yet distinguish between them. Some minds divided over the question of numbers. How many pulsars existed in the galaxy? Early estimates suggested thousands, perhaps tens of thousands. But how many were detectable, and how many more remained invisible? Either because their beams did not point toward Earth, or because they had slowed down and stopped emitting. The estimates varied widely, reflecting different assumptions about pulsar lifetimes, birth rates, and observational biases. The divide was not just scientific, it was also personal. Careers were built on being right, on defending theories, on staking claims to discoveries. Some astronomers became known as pulsar advocates, others as pulsar skeptics. Reputations were tied to positions, making it harder to change one's mind even when evidence accumulated. This is a human dimension of science often overlooked. Scientists are not purely objective machines. They have egos, ambitions, loyalties, and these shape how they interpret data. Yet, despite the divisions, progress continued. More pulsars were discovered. Better models were developed. Observations became more precise. Slowly, the evidence tilted toward the neutron star interpretation. The skeptics did not disappear, but they became fewer. The consensus grew, not because everyone agreed, but because the weight of evidence became too great to ignore. The minds that divided also collaborated. Astronomers who disagreed about mechanisms still shared data, built instruments together, co-authored papers on observations, even if they disagreed about interpretations. The divide was intellectual, not personal. Most scientists understood that disagreement was healthy, that competing ideas drove progress, that the goal was truth, not victory. And in the end, the division served a purpose. It forced the neutron star model to be tested rigorously. It prevented premature consensus. It ensured that alternative explanations were considered and ruled out. The process was slow, sometimes frustrating, but it was thorough. By the time the consensus emerged, it was built on solid ground. The divide also left a legacy. It showed that even clear observations can be interpreted in multiple ways. It reminded scientists to remain open to alternatives, to question assumptions, to demand evidence, and it demonstrated that science is not a straight path from question to answer, but a winding journey through debate, revision, and occasional dead ends. The discovery of the first pulsars sparked a race. Astronomers around the world turned their radio telescopes toward the sky, searching for more. Each new pulsar added to the catalogue, revealing patterns, variations, and clues about the nature of neutron stars. The pursuit was methodical, painstaking, and relentless. It required patience, precision, and the willingness to sift through mountains of data for rare signals. Radio telescopes, unlike optical telescopes, do not produce images in the traditional sense. They collect radio waves, the same kind of radiation used for radio broadcasts, but coming from space. The signals are faint, buried in noise, requiring sensitive receivers and careful analysis. To find a pulsar, astronomers had to scan the sky systematically, recording everything they detected, then searching for patterns in the data. The process was labor-intensive. In the late 1960s and early 70s, before computers became powerful enough to automate the search, astronomers examined paper charts by hand. Miles of paper, covered with ink traces, each line representing the signal strength at a particular frequency and time. A pulsar showed up as a repeating spike, a regular pattern standing out against the random fluctuations of background noise, but spotting it required a trained eye and hours of careful scrutiny. Jocelyn Bell had found the first pulsars this way, scanning charts late into the night, looking for anomalies. Others followed her method, combing through data with the same dedication. It was unglamorous work, tedious and repetitive, but it yielded results. Within months of the first announcement, dozens of pulsars had been discovered. Within years, hundreds. The pursuit also required innovation. Radio telescopes had to be optimized for pulsar searches. Large dishes were built, capable of detecting fainter signals. New receivers were designed, sensitive to a wider range of frequencies. Data processing techniques improved, allowing faster analysis. Each improvement expanded the reach of the search, revealing pulsars that would have been invisible to earlier instruments. One of the most important tools was timing. Pulsars did not just pulse, they pulsed with extraordinary regularity. By measuring the arrival time of each pulse with precision, astronomers could track the pulsar's rotation over months and years. This timing data revealed subtle changes, slowdowns, glitches, and wobbles, each providing clues about the pulsar's internal structure and magnetic field. The pursuit was not limited to radio waves. As technology advanced, astronomers began searching for pulsars in other wavelengths. X-ray satellites detected pulsars shining brightly in high-energy photons, often in binary systems where they were accreting matter from companion stars. Gamma-ray observatories found pulsars emitting the most energetic light known. Particles accelerated to extreme speeds by magnetic fields. Each new wavelength added a dimension to the search, revealing pulsars invisible to radio telescopes. The Crab pulsar became a focal point of study. It was bright, fast, and connected to a known supernova remnant. Astronomers observed it in every wavelength available, from radio to gamma rays, building a comprehensive picture of how it worked. The Crab became a Rosetta Stone for pulsar physics, a single object that could be studied in exquisite detail and used to test theories. But the pursuit was not just about famous pulsars. It was about building a census, cataloguing every pulsar that could be found, mapping their distribution across the galaxy. This required surveys, systematic scans of large areas of sky, searching for signals regardless of how faint or obscure. Some surveys focused on the galactic plane, where most pulsars were expected. Others searched the halo, looking for outliers. Still others targeted globular clusters, dense groups of old stars where pulsars might be recycled by binary interactions. The data accumulated slowly. Each pulsar had to be confirmed, its period measured, its position determined. False positives had to be ruled out, interference eliminated. The process required cross-checks, repeated observations, and careful analysis, but the effort paid off. By the 1980s, over 300 pulsars had been catalogued. By the 2000s, over 1,000. Today, the number exceeds 3,000. The pursuit also revealed diversity. Not all pulsars were alike. Some spun once per second, others hundreds of times. Some were isolated, drifting alone through space. Others were in binary systems, locked in gravitational dances with companions. Some emitted strong radio pulses. Others were radio quiet, but bright in X-rays or gamma rays. The variety was astonishing, suggesting that neutron stars could exist in many different states, each shaped by its history and environment. Millisecond pulsars, spinning hundreds of times per second, were among the most surprising discoveries. They were too fast to be young. Something had spun them up, revived them from slower rotation. The explanation came from binary interactions. Matter falling onto a neutron star from a companion could transfer angular momentum, spinning the neutron star faster and faster. These recycled pulsars, as they became known, were remnants with a second life, rejuvenated by their companions. The pursuit also had a human dimension. Astronomers spent careers hunting pulsars, building instruments, analysing data. Some became specialists, known for their expertise in timing, or in binary pulsars, or in millisecond pulsars. Others contributed to the infrastructure, maintaining telescopes, developing software, ensuring that the data was accurate and accessible. The pursuit was a collective effort involving hundreds of people across decades. It was also competitive. Discovering a pulsar meant publishing, gaining recognition, advancing careers. Observatories competed for time on the best telescopes. Teams raced to be the first two. Tournai, find unusual pulsars, the fastest, the most massive, the most exotic. The competition drove innovation, pushed the field forward, and occasionally created tensions. But collaboration was just as important. Data was shared, techniques exchanged, discoveries confirmed by independent observations. Pulsars found by one team were studied by others, adding detail, refining parameters. The pursuit was both a race and a partnership, individual ambition tempered by collective goals. The pursuit continues even now. New telescopes, more sensitive than ever, are being built. The Square Kilometre Array, a global network of radio dishes, will revolutionize pulsar searches, finding tens of thousands more. Each one will add to the catalogue, each one a piece of the puzzle, each one a glimpse into the physics of neutron stars. And the pursuit is not just about numbers, it is about understanding. Each pulsar tells a story about how it formed, how it evolved, how it interacts with its environment. By studying them, we learn about supernovae, about binary evolution, about the equation of state of matter at nuclear densities. The pursuit is scientific, yes, but it is also philosophical. It is about knowing the universe, about mapping the graveyard of stars, about finding beauty in the remnants of death. Every pulsar discovered was a clue, not a complete answer, but a fragment of a larger picture. Each one revealed something, a spin rate, a magnetic field strength, a location, a companion. Alone, these details might seem minor. Together, they formed a mosaic, a map of neutron star physics that grew more detailed with each observation. The first clue was timing. Pulsars arrived with clockwork precision, their periods measured to fractions of a millisecond. This precision allowed astronomers to detect tiny changes over time. The Crab pulsar, for instance, was slowing down by about 38 nanoseconds per day. A tiny change, but measurable. And it told a story. The pulsar was losing energy, radiating it away, and that energy came from its rotation. The slowdown was proof that pulsars were powered by spin, not by some internal furnace. Other pulsars showed different behaviors. Some slowed down faster, others more gradually. The rate of slowdown depended on the magnetic field strength. A stronger field meant more energy radiated, more rapid slowdown. By measuring how fast a pulsar was slowing, astronomers could infer the strength of its magnetic field. This was a powerful clue, revealing that neutron stars had fields trillions of times stronger than Earth's. Some pulsars exhibited glitches, sudden jumps in rotation rate. The pulsar would be slowing steadily, then suddenly speed up slightly before resuming its gradual slowdown. These glitches were clues to the interior structure. The leading explanation involved superfluids, frictionless liquids inside the neutron star that could store angular momentum. When the crust slowed, the superfluid continued spinning at the original rate. Eventually, the two would couple, transferring momentum and causing a glitch. Each glitch was a window into the hidden layers beneath the surface. Another clue came from binary pulsars. Some neutron stars were not alone. They orbited companion stars, sometimes other neutron stars, sometimes white dwarfs, sometimes normal stars. The orbital motion affected the pulsar's signal. As the pulsar moved toward Earth, its pulses arrived slightly earlier due to the Doppler effect. As it moved away, they arrived later. By tracking these variations, astronomers could map the orbit with extraordinary precision. The Hulse-Taylor binary pulsar, discovered in 1974, provided one of the most important clues. It consisted of two neutron stars orbiting each other every 8 hours. By timing the pulses over years, Russell Hulse and Joseph Taylor measured the orbit so precisely that they could detect its gradual decay. The two stars were slowly spiraling closer, together, losing energy. The energy loss matched exactly the predictions of general relativity for gravitational wave emission. This was the first indirect evidence that gravitational waves existed decades before they were detected directly. The clue was profound. It confirmed Einstein's theory. It showed that neutron stars could exist in pairs, and it predicted that such pairs would eventually merge, colliding in cataclysms that would shake space-time and forge heavy elements. The Hulse-Taylor pulsar was not just a curiosity, it was a laboratory for testing fundamental physics. Location was another clue. Pulsars were not distributed evenly across the sky. They clustered along the galactic plane, where massive stars lived and died. This made sense. Neutron stars formed from massive stars, and massive stars were concentrated in the disk of the galaxy. The distribution confirmed that pulsars were the remnants of stellar death, but some pulsars were found far from the plane, high above, or below the galactic disk. These were runaways, neutron stars that had been kicked by asymmetric supernova explosions. The kick could be strong enough to fling the neutron star out of the disk at hundreds of kilometers per second. These high-velocity pulsars were clues to the violence of supernovae, to the asymmetries in the explosion, to the forces unleashed when a star collapses. Magnetic field strength varied widely. Most pulsars had fields around 1 trillion Gauss, but some, the magnetars, had fields 1,000 times stronger. These extreme fields produced different behavior: intense bursts of X-rays and gamma rays, rapid slowdowns, violent eruptions. Magnetars were clues to the upper limits of magnetic fields, to the processes that could generate and sustain such extremes. Spin periods also varied. The slowest pulsars took several seconds to complete one rotation. The fastest, the millisecond pulsars, spun hundreds of times per second. This range was a clue to pulsar evolution. Young pulsars, freshly born from supernovae, started fast and slowed over millions of years. Millisecond pulsars, by contrast, were old pulsars spun up by accretion from companions. The period told you the pulsar's life story. Companion stars added more clues. Some pulsars orbited massive companions, stars that would eventually explode as supernovae themselves. Others orbited white dwarfs, the remnants of lower mass stars. Still, others orbited planets, strange worlds circling the corpse of a star. Each companion type revealed something about how the system evolved, how the neutron star formed, how it interacted over time. Radiation patterns were clues too. Some pulsars pulsed only in radio waves, others pulsed in X-rays or gamma rays. The wavelength depended on where the emission occurred, how particles were accelerated, how magnetic fields channeled them. By studying the spectrum, astronomers could infer the geometry of the magnetosphere, the structure of the emission regions, processes powering the radiation. Distances were harder to measure, but equally important. Pulsars did not come with distance markers. Astronomers had to infer distances from other clues, like the dispersion of radio signals passing through interstellar gas. The farther the pulsar, the more the signal was dispersed. This method was imperfect, but it allowed rough distance estimates. Knowing the distance turned a point on the sky into a location in three-dimensional space, revealing the pulsar's position in the galaxy. Each clue, each fragment, added to the understanding. Timing data revealed energy loss. Glitches revealed interior structure. Binary orbits revealed gravitational wave emission. Locations revealed supernova kicks. Magnetic fields revealed radiation mechanisms. Spins revealed evolutionary paths. Together, these clues formed a coherent picture of neutron stars as dynamic, evolving objects shaped by their birth conditions, their environments, and the inexorable pull physics. But the picture was incomplete. Many questions remained unanswered. What was the equation of state of neutron star matter? How exactly did glitches occur? What powered magnetar flares? How did millisecond pulsars form? Each clue answered some questions but raised others. The fragments pointed toward a fuller understanding, but the mosaic was not yet finished. And so, the search for clues continued. New pulsars were discovered. Old pulsars were studied in greater detail. Instruments improved, allowing finer measurements. Theories were tested, refined, revised. The fragments accumulated, slowly assembling into a picture of neutron stars not as static relics, but as vibrant, complex, endlessly fascinating objects at the edge of physical possibility. For decades, neutron stars were thought to be rare. The discovery of pulsars revealed their existence, but the early counts suggested only a few hundred might exist in the entire galaxy. Astronomers assumed that most neutron stars, lacking the right orientation or having slowed to silence, would remain invisible. They were curiosities, interesting but uncommon, scattered thinly across the vast expanse of the Milky Way. The hidden truth was far different. Neutron stars were not rare at all. They were abundant, perhaps numbering in the hundreds of millions. The galaxy was filled with them, a vast graveyard of collapsed stars drifting silently through space. Most were invisible, not because they did not exist, but because we lacked the tools to see them. They were dark, cold, quiet, no longer pulsing, no longer radiating, no longer announcing their presence. But they were there. The realization came gradually. As surveys improved, as telescopes became more sensitive, the number of detected pulsars grew. Hundreds became thousands. And for every pulsar found, astronomers knew there were many more that remained hidden. The geometry of pulsar beams meant that only a fraction pointed toward Earth. If a pulsar's beam swept in a different direction, it would be invisible no matter how bright it was. Calculations suggested that for every pulsar we could detect, there might be 10 or more we could not. This multiplied the population dramatically. If 3,000 pulsars were known, the true number might be 30,000 or more. And those were just the active ones. The pulsars still spinning fast enough to emit detectable radiation. Older pulsars, having slowed over millions of years, would eventually stop pulsing altogether. They would still exist as neutron stars, but they would be invisible to pulsar surveys. The hidden truth extended beyond pulsars. Some neutron stars never became pulsars at all. If a neutron star's magnetic axis happened to align with its rotation axis, it would not sweep beams across space. It would spin silently, radiating symmetrically, producing no pulses. These aligned neutron stars were invisible to traditional searches, yet they existed in unknown numbers. Others had cooled so much that they no longer emitted significant radiation. A newly formed neutron star is hot, with surface temperatures in the millions of degrees. It glows in X-rays, detectable by satellites. But over time, it cools, radiating away its heat into space. After a few million years, the surface temperature drops below the threshold of detection. The neutron star becomes a cold, dark relic, invisible in all wavelengths. The hidden truth was also revealed by supernovae. Astronomers could estimate how often massive stars exploded in the galaxy. The rate was roughly one every few decades. Over billions of years, this added up to hundreds of millions of supernovae, and each one, if the conditions were right, left behind a neutron star. Not all did. Some stars were too massive, collapsing directly into black holes. Others were too light, producing white dwarfs instead. But the majority, stars between roughly 8 and 20 solar masses, should produce neutron stars. This calculation suggested a staggering number. If the Milky Way was 10 billion years old, and supernovae occurred every few decades, and most left neutron stars, then the galaxy should contain at least 100 million neutron stars, possibly several times that. They were not rare. They were one of the most common types of stellar remnants, outnumbered only by white dwarfs. The hidden truth changed how astronomers thought about the galaxy. It was not just a collection of living stars, glowing and evolving. It was also a cemetery, filled with the remains of stars long dead. Neutron stars, white dwarfs, black holes, all drifting silently. Invisible but present, the night sky, which seemed so full of light, was actually dominated by darkness, by objects that no longer shone but still shaped the galaxy with their gravity. Some of these hidden neutron stars revealed themselves indirectly. When a neutron star passed in front of a background star, its gravity bent the light, creating a temporary brightening called gravitational lensing. These events were rare, fleeting, but detectable. They provided glimpses of neutron stars that would otherwise remain invisible. Others were found through their effects on companions. In binary systems, a neutron star's gravity could strip gas from a partner star, creating an accretion disk that glowed in X-rays. These X-ray binaries revealed neutron stars that were not pulsars, that did not sweep beams, but that were nevertheless active and detectable. Hundreds of such systems had been found, each one a hidden neutron star brought to light by its interaction with a companion. The hidden truth also applied to magnetars. These neutron stars, with their ultra-strong magnetic fields, were prone to violent outbursts. But between outbursts, they could be quiet, dormant, undetectable. Surveys had found only a few dozen confirmed magnetars, but the true number was likely much higher. Most might be sleeping, their last flare years or decades in the Faustian past, their next flare years or decades in the future. In the meantime, they drifted invisibly. The implications were profound. If neutron stars were so abundant, they played a larger role in the galaxy than previously thought. Their gravity influenced the orbits of nearby stars. Their motion contributed to the overall dynamics of the galactic disk. Their presence, even when invisible, mattered. They were not curiosities on the margins of astronomy. They were central players in the life cycle of the galaxy. The hidden truth also meant that our census was incomplete. We had found thousands, but millions remained uncatalogued. Future instruments, more sensitive and capable of detecting fainter signals, would reveal more. But even the best instruments would miss many. Some neutron stars would remain hidden forever, too cold, too old, too far, or too misaligned to be found. This realization was humbling. For all our technology, for all our surveys and catalogues, the majority of neutron stars remained unknown. We had glimpsed only the brightest, the most active, the most favourably oriented. The rest were out there, unseen, a vast population drifting through the galaxy like ghosts. But the hidden truth was not discouraging. It was exciting. It meant there was more to discover, more to learn, more surprises waiting. Each new pulsar found added to the census. Each new technique opened a window to the hidden population. Gravitational wave detectors might reveal merging neutron stars. Infrared telescopes might detect the faint glow of cooling surfaces. Neutrino observatories might catch the faint signals from supernovae births. The hidden truth also connected neutron stars to the broader universe. If the Milky Way contained hundreds of millions, then other galaxies did too. The universe was filled with them, trillions upon trillions, most invisible, most unknown, but all part of the cosmic story. They were the endpoints of stellar evolution, the products of supernovae, the forges of heavy elements, the progenitors of gravitational waves. And so, the hidden truth was both an ending and a beginning. An ending to the assumption that neutron stars were rare. A beginning to the understanding that they were common, abundant, essential. The galaxy was not what it seemed. Beneath the visible light, hidden in the darkness, was a population of collapsed stars. Silent but present, invisible but real. The graveyard was vast, far larger than anyone had imagined, and we had only just begun to map it. The discovery of millisecond pulsars in 1982 changed everything. Until then, all known pulsars were relatively slow, spinning once every few seconds at most. This made sense. Neutron stars were born spinning fast, but they slowed over time, losing energy through radiation. The oldest pulsars should be the slowest. That was the paradigm. Simple, logical, well supported by theory. Then astronomers found a pulsar spinning 642 times per second. In the blink of an eye, it completed dozens of rotations. It was impossibly fast. Far faster than any pulsar should be after millions of years of slowdown. And it was not alone. More were found, spinning hundreds of times per second, defying expectations, challenging the established model. The paradigm had to shift. Neutron stars were not simply winding down, aging gracefully into silence. Some were being spun up, rejuvenated, given a second life. The mechanism was binary interaction. A neutron star in a close orbit with a companion could accrete matter from it. As the matter spiraled inward, it transferred angular momentum, spinning the neutron star faster and faster. Over millions of years, a slow, aging pulsar could be recycled into a millisecond pulsar, spinning as fast as, or faster than when it was born. This discovery revealed that neutron stars had multiple life stages. Young pulsars, born in supernovae, started fast and slowed over time. These were the canonical pulsars, the ones that fit the original model. But in binary systems, evolution could take a different path. The neutron star could slow to near silence, then be revived by accretion, emerging as a millisecond pulsar with a second lease on life. The shift in understanding was profound. Neutron stars were not static relics. They were dynamic, evolving, shaped by their environments. A neutron star alone would age and fade. A neutron star with a companion could be transformed, spun up, and made young again. The galaxy contained both populations, each with its own history, each revealing different aspects of neutron star physics. The millisecond pulsars also had different properties. They were extraordinarily stable, their periods changing so slowly that they rivaled atomic clocks in precision. This stability made them useful as cosmic timekeepers, tools for measuring gravitational waves, testing relativity, and even navigating spacecraft. They were not just interesting objects. They were instruments. The paradigm shift also extended to magnetic fields. Young pulsars had strong fields, trillions of Gauss. Millisecond pulsars had weaker fields, billions of Gauss. The accretion process, it seemed, not only spun up the neutron star but also buried or decayed its magnetic field. This explained why millisecond pulsars behaved differently, why their radiation was less intense, why they lasted longer before fading. The discovery raised new questions. How common was recycling? How many neutron stars went through this process? Were there intermediate stages, pulsars caught mid-transformation, still accreting but not yet fully spun up? Observations suggested there were. X-ray pulsars, accreting neutron stars in binary systems, showed signs of spin-up in progress. They were the missing link, the transition stage between old pulsars and millisecond pulsars. The paradigm shift also changed how astronomers thought about stellar evolution. Binary systems were not just pairs of stars orbiting each other. They were laboratories where stars influenced each other, exchanging mass, altering each other's fates. A neutron star in a binary was not isolated. It was part of a system, its evolution intertwined with its companions. Some binary systems were violent. The neutron star, spinning rapidly, emitted radiation so intense it ablated the companion, stripping away its outer layers. These black widow pulsars, named after spiders that consume their mates, were destroying their partners even as they fed on them. The relationship was parasitic, deadly, and yet it produced some of the most exotic objects in the galaxy. Others were more stable. The companion might be a white dwarf, itself a stellar remnant, orbiting the neutron star in a dance that could last billions of years. These systems were quiet, unremarkable, but they represented the endpoint of binary evolution. Two dead stars, locked together, slowly spiraling closer as gravitational waves drained their orbital energy. The paradigm shift also highlighted the importance of mass transfer. When a companion star overflowed its Roche lobe, the region where its gravity dominated, matter spilled onto the neutron star. This matter carried angular momentum, energy, and elements forged in the companion's core. The transfer was not always steady. Sometimes it came in bursts, creating X-ray outbursts. Sometimes it was continuous, creating persistent glow. Each mode revealed different physics. The discovery of millisecond pulsars also connected neutron stars to the broader story of element creation. Accretion onto neutron stars involved high temperatures and densities, conditions where nuclear reactions could occur. Some of the accreted material was processed, fused, and ejected back into space. This contributed, though modestly, to the enrichment of the galaxy with heavy elements. The paradigm shift was not instantaneous. It took years for the full implications to be understood. Each new millisecond, pulsar added detail, confirming the recycling model, refining the parameters. By the 1990s, the picture was clear. Neutron stars had complex life cycles, shaped by birth conditions, environment, and chance. The shift also influenced the search for gravitational waves. Millisecond pulsars, stable and precisely timed, could act as a galactic network of clocks. By monitoring them over years, astronomers could detect the subtle stretching and squeezing of spacetime caused by passing gravitational waves. This technique, called pulsar timing arrays, turned the galaxy into a gravitational wave detector, sensitive to frequencies far lower than ground-based observatories could reach. The paradigm shift reminded astronomers of a fundamental truth. The universe does not always behave as expected. Models are useful, but they are simplifications. Reality is richer, more varied, more surprising. Neutron stars, once thought to follow a simple path from birth to fade, revealed themselves to be far more complex. They could be young or old, fast or slow, isolated or binary, stable or violent. Each one had its own story, and the shift continues. New discoveries still challenge assumptions, still force revisions. Magnetars, once thought to be a separate class, may be part of the same evolutionary sequence. Binary neutron star mergers, once purely theoretical, are now observed. The paradigm keeps shifting, not because the old ideas were wrong, but because the universe keeps revealing new layers of complexity. This is the nature of discovery. You build a model, test it, find exceptions, refine it. The process never ends. The paradigm never becomes final. There is always more to learn, always new data, always another surprise. Neutron stars embody this process. They are objects of extremes, pushing physics to its limits, revealing truths that could not be predicted from theory alone. And with each discovery, the paradigm shifts. the understanding deepens, and the universe becomes a little less mysterious. The confirmation that neutron stars existed sent ripples through the scientific community. Within months of the pulsar discovery, physicists were rewriting textbooks. Astronomers were redesigning observatories. Students were learning about a new class of objects that had not existed in the curriculum just years before. The immediate ripple was not just intellectual. It was practical, shaping research priorities, funding decisions, and careers. Universities began offering courses on compact objects. Neutron stars joined black holes and white dwarfs as essential topics in astrophysics. The equations governing their structure, once relegated to footnotes in specialized papers, became standard material in graduate programs. Young scientists entering the field had to understand degeneracy pressure, the equation of state of dense matter, and the physics of supernovae. Neutron stars were no longer exotic. They were fundamental. Funding agencies responded. Grants were awarded for pulsar searches, for theoretical models, for building better radio telescopes. The discovery had opened a new frontier, and resources followed. Observatories competed for time on the best instruments. Research groups formed around pulsar studies. Conferences were organized, bringing together astronomers, physicists, and theorists to share results and debate interpretations. The ripple reached beyond astronomy. Physicists studying nuclear matter suddenly had a natural laboratory. Neutron stars provided conditions impossible to recreate on Earth, densities far beyond what particle accelerators could achieve. Theorists working on quantum chromodynamics, the theory of quarks and gluons, saw neutron stars as testbeds for their models. If quarks existed in neutron star cores, as some predicted, then observations of pulsars might reveal their signatures. Relativity theorists also took notice. Neutron stars were objects where general relativity mattered. Their strong, gravity-curved spacetime slowed time, bent light. Binary pulsars, orbiting each other in tight spirals, tested Einstein's equations with precision unmatched by any laboratory experiment. The discovery that the Hulse-Taylor binary was losing energy exactly as relativity predicted was a triumph, confirming the theory in a regime far beyond what Einstein himself had imagined. The immediate ripple also influenced technology. Pulsar timing required extremely precise clocks, pushing the development of atomic standards. Radio receivers had to be sensitive enough to detect faint signals from across the galaxy, driving innovation in electronics. Data processing needed to handle vast amounts of information, spurring advances in computing. The pursuit of neutron stars indirectly contributed to technologies used far beyond astronomy. Public awareness grew. News articles described the discovery of cosmic lighthouses, objects spinning hundreds of times per second, denser than anything on Earth. Magazines published illustrations of neutron stars, artists' impressions showing glowing spheres with magnetic field lines arcing into space. The images were speculative, but they captured the imagination. Neutron stars became part of popular science, symbols of the extreme and the unknown. Educational programs adapted. Planetariums added shows about pulsars. Science museums built exhibits explaining density, showing visitors that a sugar cube of neutron star matter would weigh as much as humanity. These demonstrations, simplified but effective, introduced millions to the concept of collapsed stars. The ripple reached classrooms, where teachers used neutron stars to illustrate physics principles, from gravity to magnetism to the behavior of matter under pressure. The discovery also inspired science fiction. Writers incorporated neutron stars into stories, imagining civilizations mining their surfaces, spacecraft navigating their intense gravity, explorers studying their mysteries. Some stories were accurate, grounded in the science. Others were fantastical, using neutron stars as plot devices, but all reflected the cultural impact of the discovery. Neutron stars had entered the collective imagination. Within the scientific community, the ripple created specializations. Some astronomers focused on pulsar timing, tracking periods with microsecond precision. Others studied X-ray binaries, neutron stars accreting matter from companions. Still others modeled interiors, calculating equations of state, predicting exotic phases of matter. The field fragmented into sub-disciplines, each with its own techniques, jargon, and questions. Collaborations formed. Pulsar searches required coordination between observatories. Timing campaigns involved multiple telescopes tracking the same object over years. Theoretical work required input from nuclear physicists, particle physicists, and relativists. Neutron star research became inherently interdisciplinary, bridging fields that had previously worked in isolation. The immediate ripple also affected how astronomers thought about the life cycle of stars. Neutron stars were not endpoints. They were stages. A massive star lived, died in a supernova, and left a neutron star. That neutron star could evolve, interacting with companions, spinning up or down, eventually cooling into invisibility or collapsing into a black hole. The cycle was complex, branching, full of possibilities. Understanding it required understanding stellar evolution, binary interactions, and the final fates of matter. The discovery also raised ethical questions, though subtle ones. If neutron stars were common, and if they could host planets, as some evidence suggested, what did that mean for the possibility of life? Could life survive near such extreme objects? Probably not, given the radiation and tidal forces. But the question itself reflected a shift in thinking. The universe was larger, stranger, more varied than once believed. And if neutron stars existed, what else might be out there, waiting to be found? The ripple reached policy. Governments investing in science wanted to know what the discovery meant. Would it lead to practical applications? Probably not directly. Neutron stars were too far away to exploit. But the techniques developed to study them, the technologies, the trained scientists, these had value. The discovery justified continued investment in basic research, in telescopes, in universities. It showed that curiosity-driven science could yield profound insights. Religious communities also responded, though quietly. The existence of neutron stars, objects so extreme they defied everyday intuition, raised questions about creation, about the nature of the universe, about humanity's place in it. For some, neutron stars were evidence of divine power, of a creator capable of designing such extremes. For others, they were evidence of natural law, of physics unfolding without intent. The ripple touched worldviews, challenging and inspiring in equal measure. The immediate ripple was not uniform. Some fields were transformed, others barely touched. But the overall effect was undeniable. Neutron stars had moved from theory to reality, from speculation to observation. And in doing so, they had changed how we understood the universe, how we studied it, and how we imagined our place within it. The ripple would continue, spreading outward, influencing discoveries not yet made, questions not yet asked. But in those first years after the pulsar discovery, the immediate impact was clear. The universe had revealed something new, and we would never see it the same way again. The discovery of neutron stars did not fade. It echoed through the decades, shaping astronomy in ways both obvious and subtle. Each generation of scientists built on the work of the previous, adding detail, refining models, discovering new phenomena. The echoes were not just repetition, they were amplification. The original insight resonating in new contexts, new technologies, new questions. In the 1970s, the echoes focused on understanding pulsar mechanisms. How did magnetic fields generate beams? Where did the radiation originate? Models proliferated, each attempting to explain the observations. Some proposed emission from the magnetic poles, others from the light cylinder, where the magnetic field rotates at the speed of light. The debates were intense, but they drove progress. By the end of the decade, the broad outlines were clear, even if details remained uncertain. In the 1980s, the echoes turned to binary systems. The discovery of the Hulse-Taylor pulsar in 1974 had shown that neutron stars could orbit each other. By the 80s, more binaries were found, each revealing new physics. Some had white dwarf companions, others had normal stars, a few had other neutron stars. Each system was a laboratory, testing relativity, probing mass transfer, revealing evolutionary pathways. The 80s also brought millisecond pulsars, the recycled stars spun up by accretion. This discovery echoed the original pulsar findings, showing that neutron stars were not simple, not uniform, but diverse. The paradigm of slow, steady decline was replaced by a richer picture of multiple evolutionary paths, shaped by environment and chance. In the 1990s, the echoes extended to gravitational waves. Though not yet directly detected, the energy loss in binary pulsars provided indirect proof that gravitational waves existed. The Hulse-Taylor system was losing energy exactly as Einstein predicted, spiraling closer together over time. This echo of relativity, measurable in pulsar timing, won the Nobel Prize in 1993. It validated decades of theoretical work and set the stage for future detections. The 90s also saw the discovery of pulsar planets. A millisecond pulsar in a distant part of the galaxy showed timing variations consistent with orbiting planets. The discovery was unexpected. How could planets survive a supernova? The answer was that they probably formed afterward, from debris around the neutron star. These were strange worlds, bathed in radiation, orbiting a dead star. But they were real, echoes of planet formation in the most unlikely environments. In the 2000s, the echoes reached a crescendo with the direct detection of gravitational waves. In 2015, LIGO detected ripples in spacetime from merging black holes. 2 years later, in 2017, they detected neutron stars colliding. The signal was unmistakable. A chirp of increasing frequency as the stars spiraled together, followed by a burst of light across the electromagnetic spectrum. This was the echo of the original neutron star discovery, confirmed now in multiple wavelengths, seen and heard across the universe. The 2017 event, GW170817, was transformative. It confirmed that neutron star mergers produced heavy elements, scattering gold, platinum, and uranium into space. It showed that these collisions powered kilonovae, explosions bright enough to be seen across hundreds of millions of light years. It provided new constraints on the equation of state, narrowing the range of possible neutron star structures. The echoes of one discovery, pulsars in the 60s, had led to another, gravitational waves in the 21st century. The echoes also reached cosmology. Neutron star mergers, now observed, became tools for measuring the expansion of the universe. By comparing the gravitational wave signal with the light from the kilonova, astronomers could determine the distance to the event. This provided an independent measurement of the Hubble constant, the rate at which the universe expands. Neutron stars, once curiosities, were now cosmological probes. Through the decades, the echoes shaped technology. Each new generation of telescopes was more sensitive, more capable. Radio arrays grew larger, detecting fainter pulsars. X-ray satellites improved, resolving finer details. Gravitational wave detectors became reality, opening an entirely new way of observing the universe. The pursuit of neutron stars drove innovation, pushing the boundaries of what instruments could achieve. The echoes also influenced education. Students who learned about pulsars in the 70s became professors in the 90s, teaching the next generation. Textbooks evolved, incorporating new discoveries, new models, new understanding. The curriculum shifted, reflecting the importance of neutron stars in modern astrophysics. What had been a footnote became a central chapter. Culturally, the echoes persisted. Neutron stars appeared in documentaries, in books, in public lectures. They became symbols of the extreme, examples of how strange the universe could be. The image of a city-sized star, denser than an atomic nucleus, spinning hundreds of times per second, captured imaginations. It was a reminder that reality could be stranger than fiction. The echoes also touched philosophy. If matter could be compressed to such extremes, what did that say about the nature of reality? If neutron stars existed, stable and enduring despite their impossible densities, what else might be possible? The questions were not scientific in the narrow sense, but they were inspired by science. Echoes of discovery resonating in broader contexts. In recent years, the echoes continue. New pulsars are still being found. New binary systems are still being catalogued. New mergers are still being detected. Each adds detail. Each refines understanding. Each echoes the original discovery. The pursuit is not finished. It may never be. Neutron stars remain objects of study, sources of surprise, reminders that the universe holds more than we can yet grasp. The echoes also connect generations. Jocelyn Bell, who found the first pulsar in 1967, lived to see gravitational waves detected from neutron star collisions 50 years later. Her discovery echoed across half a century, shaping the field she helped create. Other astronomers, working in the 70s and 80s, contributed pieces that are still relevant today. The echoes are not just temporal, they are personal, connecting individuals across time through shared curiosity and effort. And the echoes will continue. Future telescopes will find more neutron stars. Future detectors will catch more gravitational waves. Future theories will explain more details. Each will echo the past, building on what came before, adding to the story. The discovery of neutron stars was not an event. It was a beginning, a note struck that continues to resonate, shaping astronomy, physics, and our understanding of the universe. The echoes through time are not fading. They are growing, deepening, reaching into futures we cannot yet see. Behind every discovery are the dreamers, the people who devoted lifetimes to questions that might never be answered, who built instruments that might never work, who searched for signals that might not exist. The story of neutron stars is filled with such people. Their names, sometimes famous, often forgotten, but their contributions essential. Walter Baade and Fritz Zwicky, who proposed neutron stars in 1934, were dreamers in the truest sense. They imagined something that seemed impossible, something that no one had observed, something that defied common sense. Zwicky, in particular, was known for bold, often outrageous ideas. He proposed dark matter, supernovae, as distinct events, and neutron stars, all before there was evidence for any of them. But he was right more often than not, and his dream of neutron stars eventually became reality. Jocelyn Bell Burnell was a dreamer of a different kind. As a graduate student, she spent months scanning paper charts, looking for anomalies in radio data. The work was tedious, repetitive, unglamorous. Most would have missed the signal, dismissed it as noise, moved on. But Bell noticed, pursued it, found more. Her dream was not of neutron stars specifically. She had been studying quasars, but of discovery, of finding something new. And she did. Anthony Hewish, her supervisor, dreamed of building instruments that could reveal the invisible, His radio telescope was not the largest or most powerful, but it was designed to detect rapid variations in radio signals. That design, that dream of seeing what others could not, made the pulsar discovery possible. Without the right tool, the signal would have remained hidden. Russell Hulse and Joseph Taylor, who discovered the binary pulsar, were dreamers who believed in precision. They spent years timing a single pulsar, measuring its period to within microseconds, tracking its orbit with painstaking care. Their dream was not glory but understanding, not headlines but data, and their patience paid off. The orbital decay they measured, just fractions of a second over years, provided the first evidence of gravitational waves. Their dream of precision became proof of Einstein's theory. There were others, less famous but no less important. The technicians who maintained telescopes, ensuring they operated flawlessly night after night. The programmers who wrote software to process data, turning raw numbers into meaningful results. The students who spent years on projects that might not lead anywhere, who analyzed data, ran simulations, tested models. Each was a dreamer, contributing to a collective effort. Some dreamers faced obstacles. Jocelyn Bell, despite her crucial role in the pulsar discovery, was not awarded the Nobel Prize. The prize went to Hewish, her supervisor, and to Martin Ryle, who had developed radio astronomy techniques. Bell's omission sparked debate that continues today. She handled it with grace, continuing her career, mentoring young scientists, advocating for women in science. Her dream was not recognition but discovery, and she achieved that regardless of prizes. Fritz Zwicky faced different obstacles. His abrasive personality alienated colleagues. His ideas, often ahead of their time, were dismissed. He worked in relative isolation, driven by conviction that he was right even when others disagreed. His dream of understanding the universe's extremes sustained him through decades of skepticism. And in the end, many of his ideas were vindicated. Other dreamers worked in teams, building collaborations that spanned institutions and countries. The gravitational wave detectors, LIGO and Virgo, were the products of thousands of scientists, engineers, and technicians working together over decades. Each contributed a piece. Each shared the dream of detecting ripples in space-time. When the first detection came in 2015, it was a collective triumph, the realization of a dream that had begun in the 1960s. The dream of understanding Neutron. Stars also inspired theorists. Subramanian Chandrasekhar, who calculated the limits of white dwarf masses, laid groundwork for understanding stellar collapse. His work, done in the 1930s, predicted that stars above a certain mass could not be supported by electron degeneracy. This opened the door to neutron stars and black holes, though Chandrasekhar himself focused on white dwarfs. His dream of understanding stellar structure shaped the field. J. Robert Oppenheimer, before his work on the atomic bomb, studied neutron stars and black holes. In 1939, he and his student George Volkoff calculated the structure of neutron stars, showing that they could exist but only within a narrow mass range. Oppenheimer's dream was to understand the fundamental physics of collapsed matter. His work, though largely forgotten during the war years, became foundational when pulsars were discovered decades later. The dreamers also included those who built instruments without knowing what they would find. The radio astronomers who constructed large arrays, the satellite designers who launched X-ray observatories, the engineers who built gravitational wave detectors. Each dreamed of discovery, of finding something new, even if they could not predict what it would be. Their openness to surprise, their willingness to invest in tools for unknown purposes, made many discoveries possible. And there were the dreamers who failed, whose projects did not work, whose ideas did not pan out, whose careers did not flourish. Science is filled with such people, their names lost, their contributions forgotten. but they were part of the process, testing ideas, exploring dead ends, clearing paths for others. Their dreams, though unrealized, were no less important. The dream of understanding neutron stars continues. Today's astronomers, building on the work of previous generations, search for new pulsars, study binary systems, detect gravitational waves. They dream of measuring the equation of state, of finding quark matter, of detecting continuous gravitational waves from spinning neutron stars. Each dream builds on those that came before. Students entering the field today stand on the shoulders of dreamers they will never meet. Bardet and Zwicky, Bell and Hewish, Hulse and Taylor, and countless others. The lineage of dreams stretches back decades, connecting past and future. Each dreamer added a piece, each contributed to the understanding, each helped map the territory of neutron stars. The dreamers remind us that science is not impersonal. It is deeply human, driven by curiosity, passion, stubbornness, and hope. The equations and data are important, but behind them are people who cared, who wondered, who refused to give up. Neutron stars were discovered because people dreamed they might exist, searched for evidence, built tools, analyzed signals. The dream came first. The discovery followed. Even after pulsars were discovered, even after their properties were measured, even after the evidence accumulated, resistance remained. Not everyone accepted that neutron stars existed. Not everyone believed the models. The battle for truth was not fought in laboratories or observatories alone, but in journals, conferences, and quiet conversations where skeptics voiced doubts and defenders marshalled evidence. Some of the resistance was scientific. The densities required for neutron stars seemed absurd. How could matter be compressed to the point where a teaspoon weighed 1 billion tons? The calculations suggested it was possible, but calculations could be wrong. Equations were abstractions. The real universe, messy and complex, did not always follow theoretical predictions. Some physicists argued that there must be another explanation, some mechanism that prevented such extreme compression. Others questioned the pulsar mechanism. How could magnetic fields generate such regular pulses? How could a star spin hundreds of times per second without flying apart? The models seemed ad hoc, constructed to fit observations rather than derived from first principles. Some argued that pulsars might be something else entirely, perhaps oscillating white dwarfs, perhaps binary systems with unusual geometries, perhaps phenomena not yet understood. The skeptics demanded more evidence. They wanted to see neutron stars directly, not just infer them from radio pulses. They wanted independent confirmation, multiple lines of evidence, proof that could not be explained away. And to some extent, their demands were reasonable. Extraordinary claims required extraordinary evidence. Neutron stars were extraordinary, but the evidence kept accumulating. The Crab pulsar, located in a known supernova remnant, provided a clear connection between supernovae and neutron stars. The slowdown of pulsars, measured with precision, confirmed that they were losing energy through rotation. The discovery of binary pulsars showed that neutron stars could exist, in pairs, orbiting each other in ways that matched theoretical predictions. Each piece of evidence answered one objection, only to be met with another. Some resistance was institutional. Established astronomers, trained in an era before neutron stars were known, found it difficult to accept such radical objects. Their careers had been built on understanding normal stars, galaxies, nebulae. Neutron stars did not fit into familiar categories. They required new physics, new models, new ways of thinking. For some, it was easier to doubt than to adapt. Younger scientists faced resistance too. Students proposing to study neutron stars were sometimes discouraged. Why focus on such speculative objects? Why not work on something more established? more likely to yield results, some advisors refused to support neutron star research, seeing it as a distraction from more important questions. Careers were shaped, sometimes derailed, by these institutional barriers. The battle also played out in funding. Research on neutron stars required expensive instruments, radio telescopes, X-ray satellites, supercomputers for simulations. Agencies had to decide whether to invest in this new field or to support more traditional astronomy. Some chose to invest, others did not. The balance shifted over time as evidence mounted and skepticism faded. But the early years were uncertain. The resistance was not always overt. Sometimes it took the form of silence. Papers on neutron stars were published, but not widely cited. Discoveries were announced, but not followed up. The field advanced, but slowly, hampered by lack of attention and resources. This quiet resistance was harder to combat than open skepticism. There was nothing to argue against, just an absence of interest. But the defenders of neutron stars persisted. They published more papers, presented more evidence, built more instruments. They organized conferences, bringing together researchers to share results and coordinate efforts. They trained students, passing on knowledge and enthusiasm to the next generation. Slowly, the resistance crumbled. The Hulse-Taylor binary pulsar was a turning point. The orbital decay, matching gravitational wave predictions exactly, was too precise to be coincidence. Even the most hardened skeptics had to acknowledge that something remarkable was happening. The system behaved exactly as it should if it contained two neutron stars orbiting each other. The evidence was overwhelming. The Nobel Prize in 1993, awarded for the binary pulsar discovery, was another milestone. It signaled that neutron star research had arrived, that it was not speculative but established, not fringe but central. The prize did not end all resistance, but it legitimized the field in the eyes of the broader scientific community. X-ray observations also helped. Satellites detected neutron stars in binary systems, accreting matter from companions, glowing brightly in high-energy photons. These observations provided visual confirmation, images, and spectra that showed neutron stars were real, active, and exactly where theory predicted. The skeptics could no longer argue that neutron stars were invisible, inferred only from timing data. They could be seen, at least in X-rays. The battle for truth also involved public understanding. Communicating the nature of neutron stars to non-scientists was challenging. How do you explain densities beyond imagination? How do you convey the precision of pulsar timing? How do you make people care about objects so remote and abstract? Science writers, educators, and astronomers worked to translate the discoveries into accessible language using metaphors, analogies, and visualizations. The effort helped build public support, which in turn influenced funding and institutional priorities. But resistance lingered in subtle forms. Even as neutron stars became accepted, debates continued about details. What was the equation of state? Did quark matter exist in cores? How did magnetar flares work? These were not arguments about whether neutron stars existed, but about how they worked. The battle shifted from existence to mechanism, from gross properties to fine details. Some of this ongoing debate was healthy. Science thrives on skepticism, on questioning, on demanding evidence. The challenge is to distinguish productive skepticism from stubborn resistance. Productive skepticism asks for better data, tests predictions, refines models. Stubborn resistance rejects evidence, clings to outdated ideas, refuses to engage. The history of neutron stars includes both. The battle for truth was also personal. Careers rose and fell based on positions taken. Those who embraced neutron stars early gained opportunities as the field expanded. Those who resisted were sometimes left behind, their expertise in other areas less valued as neutron star research became central. This created tensions, resentments, and occasionally bitter disputes. But in the end, truth won. Not because everyone was convinced, but because the evidence became too strong to ignore. Neutron stars existed. They behaved as predicted. They were real, measurable, understandable. The skeptics faded, either convinced or retired. The field moved on, no longer fighting for acceptance but pushing for deeper understanding. The battle for truth was necessary. It forced proponents to be rigorous, to check assumptions, to gather better data. It ensured that the acceptance of neutron stars was based on solid ground, not wishful thinking. And it demonstrated that science, for all its flaws, eventually converges on reality. The process is slow, messy, contentious, but it works. Something shifted in the collective understanding. Not all at once, not for everyone, but gradually, over years and decades, a new awareness took hold. Neutron stars were not just astronomical curiosities. They were laboratories for extreme physics, test beds for fundamental theories, windows into the behavior of matter under conditions impossible to recreate on Earth. To study them was to study the universe at its most extreme. This awareness changed how scientists approached neutron stars. Early on, they were objects to catalogue, phenomena to explain. Pulsars pulsed. That was interesting. But as understanding deepened, neutron stars became tools. Their timing could test relativity. Their oscillations could probe interior structure. Their mergers could reveal the origins of elements. The shift was from passive observation to active interrogation. Neutron stars were not just things to look at. They were questions to ask. The awareness extended to the broader implications. If matter could be compressed to such densities, what did that reveal about the fundamental forces? Gravity, obviously, but also the strong nuclear force that held neutrons together. At neutron star densities, nucleons might break down into quarks, forming exotic phases of matter, or they might remain intact, held by forces we did not yet fully understand. The uncertainty was not a failure. It was an opportunity. Neutron stars could teach us about physics beyond the reach of accelerators. General relativity also benefited. Einstein's equations predicted how space-time should behave near massive objects, but testing those predictions required extreme conditions. Neutron stars provided them. Their strong gravity curved space, slowed time, bent light. Binary pulsars orbiting each other tested relativity with precision unmatched by solar system experiments. Every observation confirmed Einstein's predictions, but the real value was in the precision. The more accurately we measured, the more confidence we gained, or the more clearly we would see if deviations appeared. The awareness also touched cosmology. Neutron star mergers, now detected through gravitational waves, provided a new way to measure the expansion of the universe. The gravitational wave signal revealed the masses and distance. The electromagnetic signal revealed the redshift. Together, they gave an independent measurement of the Hubble constant, the rate at which space expands. This was not the primary goal when neutron stars were first discovered, but it showed how foundational discoveries could lead in unexpected directions. For nuclear physicists, the awareness was transformative. The equation of state of neutron star matter, the relationship between pressure and density, depended on nuclear forces at extreme conditions. Different models predicted different equations of state, and those predictions could be tested by observing neutron stars. The maximum mass a neutron star could support, for instance, depended on how stiff the equation of state was. By measuring the masses of the heaviest neutron stars, astronomers constrained the models, narrowing the range of possibilities. The awareness also influenced how we thought about life in the universe. Neutron stars with their intense radiation and gravity, seemed hostile to life, but they played a role in creating the conditions for life elsewhere. Their supernovae scattered heavy elements into space. Their mergers forged gold, platinum, and other elements essential for complex chemistry. Without neutron stars, the universe would be poorer, simpler, less capable of supporting the diversity of matter we see. This awareness reached philosophy as well. What did it mean to live in a universe where stars could collapse into objects so dense that atoms were destroyed, where matter could exist in states unlike anything in daily experience, where the laws of physics, when pushed to extremes, produced results that defied intuition? Neutron stars were reminders that reality was not limited by what we could easily imagine. The universe was larger, stranger, more varied than human experience suggested. The new awareness also shaped education. Students learned about neutron stars not just as examples of stellar remnants, but as entry points into deeper topics. Studying neutron stars meant learning about quantum mechanics, relativity, nuclear physics, and thermodynamics. They were multidisciplinary objects, requiring knowledge from many fields. This made them ideal for teaching, for showing how different areas of physics connected. Culturally, the awareness filtered into broader consciousness. Neutron stars appeared in documentaries, in books, in public lectures. They became symbols of the extreme, examples of how strange the universe could be. The phrase denser than a neutron star entered the lexicon, a metaphor for ultimate compression. People who had never studied astronomy knew that neutron stars existed, that they were strange, that they mattered. The awareness also brought humility. Neutron stars reminded us how much we did not know. Despite decades of study, fundamental questions remained unanswered. What exactly happened inside them? How did magnetar flares work? Could continuous gravitational waves be detected? Each answer led to new questions, each discovery to new mysteries. The awareness was not of complete understanding, but of the vastness of what remained to be understood. For those who studied neutron stars, the awareness was personal. These were not abstract objects. They were real, out there in the galaxy, spinning, radiating, sometimes colliding. To detect a pulsar, to time its pulses, to measure its properties, was to connect with something beyond human scale. It was humbling and exhilarating, a reminder that the universe held wonders far beyond everyday life. The awareness also fostered collaboration. Neutron stars could not be understood by one person or one field. They required astronomers, physicists, mathematicians, engineers. They required radio telescopes, X-ray satellites, gravitational wave detectors. They required theorists to model, observers to measure, experimentalists to test. The complexity demanded teamwork, and the teamwork produced results impossible for individuals alone. And the awareness continues to grow. Each new detection adds to it. Each new measurement refines it. Each new theory deepens it. Neutron stars are not fully understood, and perhaps they never will be. But the awareness of their importance, their utility, their beauty, is now woven into the fabric of astrophysics. They are not footnotes. They are central, essential, irreplaceable. To study the universe without studying neutron stars would be to miss something fundamental, something that reveals truths about matter, gravity, and the nature of reality itself. The deepest truth about neutron stars is simple to state but profound to grasp. They are the densest objects in the universe that are not black holes. They exist at the very edge of physical possibility, balanced on a knife's edge between existence and collapse. Add a little more mass, and they would cross the threshold, disappearing behind an event horizon. Remove a little, and they would expand, becoming white dwarfs instead. Neutron stars occupy the narrow boundary, the limit of what matter can endure. This truth has implications for everything we know about physics. It means that matter, compressed to the point where atoms are destroyed, can still resist further collapse. The resistance comes from quantum mechanics, from the Pauli exclusion principle that prevents neutrons from occupying the same state. This is not a force in the ordinary sense. It is a statistical rule, a consequence of the nature of particles, and yet it is strong enough to hold up the weight of a star. The deepest truth also concerns the interior. No one knows for certain what lies at the center of a neutron star. The densities are so extreme that our theories become uncertain. Some models predict neutrons packed tightly together, held by nuclear forces. Others predict that neutrons break down into quarks, forming quark matter. Still others propose exotic particles, hyperons, or strange matter, governed by forces barely understood. Each model makes predictions. The equation of state, the relationship between pressure and density, differs depending on what happens inside. And the equation of state determines observable properties like maximum mass, radius, and how the star responds to tidal forces. By measuring these properties, astronomers can test the models, ruling out some, constraining others. But the deepest interior remains hidden, accessible only through inference. The truth also involves time. Neutron stars are not eternal. They are born in supernovae, live for billions of years, and eventually fade or transform. Young neutron stars are hot, spinning rapidly, radiating intensely. Over time, they cool, slow, and dim. Eventually, they become dark, cold, invisible. Or they accrete matter from companions, spinning up into millisecond pulsars. Or they merge with other neutron stars, collapsing into black holes and scattering heavy elements into space. The life cycle is complex, branching, shaped by initial conditions and chance encounters. No two neutron stars follow identical paths. Each has its own history, its own fate, and yet they all share the same fundamental truth. They are matter pushed to its limit, existing in a state that defies everyday experience. The deepest truth also touches on stability. Neutron stars are stable, but only within a narrow mass range. Too light, and they cannot form. The core of the collapsing star does not have enough mass to crush atoms into neutrons. Instead, it becomes a white dwarf, held up by electron degeneracy pressure. Too heavy, and neutron degeneracy pressure fails. Nothing can stop the collapse, and a black hole forms. The range where neutron stars exist is narrow, between roughly 1.4 and 2.5 solar masses. This narrow range has been measured through observations of binary systems. Neutron stars in binaries can have their masses determined with precision by measuring orbital dynamics. The results cluster within the expected range, confirming the theory. But the upper limit, the maximum mass a neutron star can support, remains uncertain. Different equations of state predict different limits. Observations narrow the range, but do not yet provide a definitive answer. The truth also involves rotation. Neutron stars can spin incredibly fast, but there is a limit. If they spin too quickly, centrifugal forces overcome gravity, and the star flies apart. The fastest known pulsars spin about 700 times per second, well below the theoretical limit. This suggests that something prevents them from spinning faster. Perhaps the accretion process that spins them up becomes unstable. Perhaps they emit gravitational waves that carry away angular momentum. The exact mechanism is still debated. Magnetic fields add another layer. Neutron stars have the strongest magnetic fields known, but again, there are limits. Fields stronger than a certain threshold might alter the structure of the crust, triggering instabilities. Magnetars, with their ultra-strong fields, show signs of such instabilities, erupting in violent flares. The fields may also decay over time, weakening as the star ages. The interplay between field strength, rotation, and structure is complex, still not fully understood. The deepest truth is also about what neutron stars teach us. They are natural experiments, testing physics at conditions we cannot replicate. Every observation, every measurement, adds to our knowledge of how matter behaves under extreme pressure, how gravity warps space-time, how magnetic fields shape radiation. Neutron stars are not just objects to study. They are teachers, revealing truths about the universe that we could not learn any other way. And the truth is humbling. Despite decades of study, fundamental questions remain. What is the equation of state? How do magnetar flares work? Can we detect continuous gravitational waves from spinning neutron stars? Each question is a frontier, a challenge, an opportunity. The deepest truth is not that we have all the answers. It is that neutron stars provide the questions worth asking. The truth also involves beauty. Not aesthetic beauty, though images of pulsars and supernovae can be stunning, but the beauty of simplicity, of elegance. Neutron stars are governed by the same laws as everything else. Gravity, quantum mechanics, electromagnetism. No special rules, no exceptions. And yet, from those simple laws, complexity emerges. Pulsars, magnetars, binary systems, mergers. The richness arises from the interplay of forces, the balance of extremes, the edge of possibility. The deepest truth is that neutron stars exist. Against all odds, against intuition, against the limits of imagination, they are real. You can point a telescope at one, measure its pulses, track its orbit, watch it evolve. The universe has created objects so extreme they challenge understanding, and it has placed them within reach of observation. That is the deepest truth. Not just that neutron stars are strange, but that they are knowable. What does it mean to live in a universe where neutron stars exist? Where matter can be compressed beyond atoms, where gravity can warp time, where magnetic fields can reach strengths that distort space itself. The question is not scientific, but philosophical. It asks not how neutron stars work, but what their existence tells us about reality, about our place in it, about the nature of knowledge and limits. To ponder neutron stars is to confront scale. A teaspoon of neutron star matter weighs 1 billion tons. The number is so large it loses meaning. We cannot hold it, cannot feel it, cannot truly imagine it, and yet it is real. Somewhere in the galaxy, matter exists in this form, compressed to densities our minds cannot grasp. The meaning is that the universe does not care about human intuition. It operates according to laws that produce results far beyond everyday experience. The meaning also touches on fragility. We live on a planet where matter is stable, where atoms hold together, where chemistry follows predictable rules. But this stability is contingent. Under different conditions, matter behaves differently. In a neutron star, atoms are destroyed. Chemistry does not exist. The familiar structure of electrons and nuclei gives way to a sea of neutrons. The meaning is that the world we know is a narrow slice of possibility, a special case in a universe capable of far more variety. To ponder neutron stars is also to ponder endings. Every neutron star is the remnant of a massive star that died. The star lived, burned, and collapsed. What remains is not the star itself, but its core, transformed beyond recognition. The meaning is that endings are not always final. They can be transformations, transitions into something new. Death, in the cosmic sense, is not annihilation, but change. And yet, even the transformed star eventually fades. Neutron stars cool, slow, and disappear into darkness. or they collide, destroying themselves and creating something else. The meaning is that impermanence is universal. Nothing lasts forever, not planets, not stars, not even the densest objects in existence. Everything changes, everything evolves, everything eventually ends. The meaning also involves perspective. From Earth, neutron stars are invisible points in the sky. From up close, they are vast, overwhelming, deadly. The truth depends on where you stand. The meaning is that perspective shapes reality, that observation is limited by position, that what we know is always partial. Neutron stars remind us to question our assumptions, to recognize that our view is not the only view. To ponder neutron stars is also to ponder limits. They exist at the edge of what is possible, denser, and they would become black holes. Less dense, and they would not exist at all. The meaning is that the universe has boundaries, thresholds where one thing becomes another. These boundaries are not arbitrary. They are defined by the laws of physics, by the fundamental forces that govern reality. To study neutron stars is to study those boundaries, to understand where matter ends and something else begins. The meaning also concerns connection. Neutron stars are made of the same particles as everything else. Neutrons exist in ordinary atomic nuclei. The difference is quantity, density, arrangement. The meaning is that the extreme and the familiar are not separate. They are connected, part of a continuum. What happens in a neutron star is not alien, just magnified, intensified, pushed to limits we do not encounter daily. To ponder neutron stars is also to ponder beauty. Not visual beauty, though their geometry is elegant, but the beauty of understanding, of pattern, of law. Neutron stars obey the same equations as falling apples or orbiting planets. The laws scale, from the small to the large, from the gentle to the extreme. The meaning is that the universe is coherent, that knowledge is possible, that understanding one thing can illuminate another. The meaning also involves humility. Neutron stars exist regardless of whether we understand them. They were spinning, radiating, colliding long before humans existed. They will continue long after we are gone. The meaning is that the universe does not depend on us. Our knowledge, while valuable, is not necessary for reality to unfold. We are observers, not participants. Our role is to watch, to learn, to appreciate. And yet, there is also empowerment. We can understand neutron stars, despite their remoteness, despite their extremes. We can measure them, model them, predict their behavior. The meaning is that human minds, limited as they are, can grasp truths about the universe. We are small, but we are capable. Our knowledge is incomplete, but it is real. To ponder neutron stars is also to ponder mystery. For all we know, fundamental questions remain unanswered. What happens at the very center? How do magnetar flares work? What is the equation of state? The meaning is that knowledge is always provisional, always incomplete. There is always more to discover, always deeper layers, always new questions. The meaning also extends to wonder. Neutron stars are astonishing. That they exist at all is remarkable. That we can study them is miraculous. The meaning is that the universe is generous, revealing its secrets to those who look carefully, who ask questions, who persist. Wonder is not just an emotion. It is a response to reality, to the fact that the universe holds more than we can imagine. To ponder neutron stars is to ponder our own existence. We are made of atoms, forged in stars. Some of those atoms came from supernovae that left neutron stars behind. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created in stellar furnaces. The meaning is that we are connected to neutron stars, not just intellectually but physically. We carry the universe within us. And, finally, to ponder neutron stars is to accept that some things are beyond full comprehension. We can measure, model, predict. But the experience of being near one, the reality of such density and gravity, is beyond human capacity. The meaning is that knowledge has limits, that understanding is not the same as experiencing, that some truths can only be approached, never fully grasped. It is the nature of existence in a universe far larger and stranger than ourselves. The neutron stars will endure, long after the last human voice falls silent, long after Earth itself is gone, they will continue, spinning in darkness, cooling slowly, drifting through the galaxy. Some will collide, creating bursts of light and gravitational waves. Others will fade into invisibility, cold and dark. But they will persist, monuments to the death of stars, testaments to the resilience of matter under extreme conditions. This is the legacy, not what we have learned, though that is significant, but the fact that neutron stars exist at all, that the universe produces such objects, that nature permits such extremes. The legacy is written in the stars themselves, in their spin, their density, their magnetic fields. It is a legacy that predates humanity and will outlast it. The legacy also includes the knowledge we have gained. From the first pulsar discovered in 1967 to the gravitational waves detected decades later, each observation has added to our understanding. We know that neutron stars form in supernovae. We know they can spin hundreds of times per second. We know they can merge, forging heavy elements. We know they test relativity, probe nuclear physics, reveal the equation of state of dense matter. This knowledge is part of humanity's intellectual legacy, passed from generation to generation. The instruments we built are also part of the legacy. Radio telescopes that detected the first pulsars, X-ray satellites that revealed accreting, neutron stars, gravitational wave detectors that felt the ripples of mergers. Each instrument extended our senses, allowing us to see, hear, and measure what would otherwise be invisible. The technology will evolve, but the principle remains. We reach beyond our natural limitations to grasp truths about the universe. The legacy includes the questions still unanswered. What is the maximum mass? What happens in the core? Can we detect continuous gravitational waves? These questions are gifts to future scientists, challenges to pursue, mysteries to unravel. The legacy is not closure, but continuation. Each answer leads to new questions, each discovery to new frontiers. And now, as this journey through neutron stars comes to an end, it is time to return. Not to leave neutron stars behind, that is impossible, but to return to the immediacy of the present, to the quiet of the moment, to the awareness of being here, now, in this place and time. The return begins with a breath. Slow, deep, filling the lungs, then releasing. The neutron stars are far away, spinning silently in the darkness. You are here, grounded, present. The vast distances shrink, the extreme densities fade. What remains is the simple fact of existence, of awareness, of being alive in a universe that contains such wonders. Look up, if you can. See the night sky, the familiar stars. Know that among them, invisible to the eye, are neutron stars. They do not announce themselves, they do not demand attention, but they are there, part of the same sky, part of the same galaxy, part of the same story. You are inside the Milky Way, surrounded by remnants of stars that died billions of years ago. The return is also a letting go. You cannot hold the density of a neutron star in your mind. You cannot grasp the full scale, the full extremity. Let it be vast. Let it remain partly unknowable. That is its nature. What you can hold is the awareness that such things exist. that the universe is capable of producing them. That reality extends far beyond everyday experience. What remains is the simple truth. Neutron stars are the densest objects that are not black holes. They are the edge of possibility, the limit of matter. They spin, they radiate, they collide. They teach us about physics, about the universe, about the nature of reality, and they endure. Long after stars like our sun have burned out, long after galaxies have evolved, long after the universe has aged in ways we cannot yet predict, the legacy of neutron stars is not just scientific, it is philosophical, cultural, human. They remind us of our smallness, but also of our capacity. We are tiny, yes, but we can understand, we can measure, we can know. That is remarkable. That is the legacy we carry forward. And as the story closes, the tone softens. The neutron stars fade into the background. They remain, but quietly. The focus shifts back to you, to the present, to the moment. You have travelled through the life and death of stars, through densities beyond imagination, through magnetic fields that warp space. You have glimpsed the edge of physical possibility. And now, you return. You can rest now. The universe will continue without your attention. The neutron stars will keep spinning, the pulsars will keep pulsing, the galaxy will keep turning. You do not need to hold it all in your mind. You can let it go, knowing that it exists, knowing that it is real, knowing that it will be there tomorrow and the day after. The return is complete. You are back where you started, in the quiet of the night, under the stars, but you see them differently now. Not just as lights, but as part of a vast system that includes neutron stars, black holes, supernovae, and the slow cycle of stellar birth and death. You are part of that system, made of its matter, shaped by its history. The neutron stars endure, and so does the journey of understanding them. That journey is not finished. It will continue as long as there are minds to wonder, eyes to observe, instruments to measure. The legacy is not an endpoint, but a beginning. An invitation to future generations to keep looking, keep questioning, keep discovering. For now, rest, breathe, and know that you are home. Here, inside the galaxy, under the stars, surrounded by wonders you can know but never fully hold. The neutron stars are out there, spinning in silence, ancient and deadly, patient and enduring, and that is enough.